And anybody have any questions about anything other than what already was stated? I guess I'll repeat that it's recording. Question was do the metals, like as the reaction is going, the electrochemical reaction is going, and the anode is corroding away and the cathode is increasing in size, does it affect the voltage? And the answer is no, it does not. What does affect the voltage though is the question specifically asked about the metals. It's the concentration of the ions in solution. So the concentration of the ions will affect the voltage, and we'll talk about that either today or on Monday. Other question is, will heating, the metals expand upon heating? Will the heat affect the weight? And the answer is no, it just changes the density. So, other questions? All right, so last class, we were talking quite a bit about this. I gave my introduction of sorts to electrochemistry, and I talked about this voltaic cell, sometimes called a galvanic cell. And here are the features of the standard, and this is for a standard cell. So let me erase a lot of this. Actually, I can keep that, that's the voltage. So this here written is a standard cell, meaning it's at 25 degrees Celsius. You have the metals of interest, and you have solutions at 1 molar. I guess I can write this down. So we have 25 degrees Celsius. So, and this is 1 molar zinc, 1 molar copper ion. So everything is at 1 molar and at 25 degrees Celsius. And when that happens, we get the E0 cell. So, and if you've noticed, and maybe you've noticed in your class, you know, it's always nice to have a really smart friend, right? Especially when you don't know what's going on, because then you can copy all the smart friend's homework, right? Kind of like I've been reading a lot on the internet about Harry Potter. It's one of my favorite things. Like Hermione Granger was always a smart friend that Harry and Ron always copied off of. So it's always, am I too old? Is Harry Potter no longer relevant to you guys, or is that still relevant? I don't know. Okay, good. I forget sometimes. I don't know. Since my birthday, my eyes are starting to go. I'm like, man, how old am I? Okay, Harry Potter's still cool. Awesome. So, you know, just like how Hermione was the smart friend, they copied the homework. We have smart friends too, like Gibbs, who I talked about last chapter. And our smart friends have gone ahead and calculated out all, or done these experiments, and now have all the standard cells. So I can switch to orientation. Okay, yes, but I need to do the full screen again. So, oh, I guess you can't see this as well. So here is everything. Here are all the standard, these are the standard electrode potentials at 25 degrees Celsius, and further broken down into half reactions. And these are written as reduction. So reduction is adding electrons. And we pick a reference, and the reference we've decided to pick is hydrogen. If you can see, I guess you can't see that. So I'll go ahead and switch back to landscape. So we have our reference. Can you see? Okay, so our reference set 0 is 2 hydrogen ion acids plus 2 electrons makes hydrogen gas, and we're going to give that we're going to have that be our reference point. So kind of like in so for enthalpies, so we pick elements, things in a specific element for if there's more than one specific state. It's like, so carbon, I mean, there's a couple of different types of carbon. There's graphite, there's diamond that are both common. There's the the fullerene, C60, C70. There's nano rods of carbon. So there's graphene. So what do we pick? We pick graphite. So I picked the easiest one. So we picked the easiest one. So there's a rhyme and reason for this. And we pick hydrogen as our reference point. And this is for a few reasons. First of all, anything above, any metal that you find above hydrogen does not readily dissolve in acid. So that's a nice, easy check. Anything that's got a positive E0 metal, you know, it's not going to dissolve in acid. So that's an easy thing. And then then it's just, we just pick that, like I said, as our reference point. It just seemed to be convenient, among other things. So we're going to be doing some calculations soon, and the electric potential, the voltage of the cell, the E0 cell, is the oxidation potential plus the reduction potential. And the oxidation potential is opposite the reduction potential. So meaning, if you look here at the top, fluorine plus 2 electrons yields 2 fluorides. The top one, the potential for that reaction is 2.87 volts. So the opposite direction, 2 fluorides going to fluorine plus 2 electrons, that oxidation reaction, the potential for that is negative 2.87 volts. So, and fluorine is at the top, and at the top is the strongest oxidizing agent. So fluorine is the strongest oxidizing agent. And then we have all the way on the bottom, you have lithium. So hydrogen's in the middle, and then the bottom there, lithium is the weakest oxidizing agent, but it's the strongest reducing agent. So lithium plus electrons reduced to form lithium metal. That potential is negative 3.04 volts. So which means the other way around, lithium going to lithium ion plus electrons, that's positive 3.0 volts. So lithium is really good for batteries, and not surprisingly, right? We have lithium, that's one of the coveted metals. I mean, I guess it shows our ages. I mean, so if I asked my siblings and if I said the word lithium, what would they think about? They'd probably think about a Nirvana song called Lithium. So yeah, Nirvana. But if I asked you guys, if I said the word lithium, you know, what's the first thing that comes to mind? Batteries, yes. Yeah, lithium batteries. So we use lithium quite a bit in batteries. And I also want to point out, this is the electromotive force when it comes to each atom and the electrons in the atoms. So if you look at the activity series of metals, so if I had a bucket of water, and I'm not going to do this because we don't have all the elements, first of all, and secondly, it's a little dangerous and a pain to clean up. But lithium, if you drop lithium in the water, it'll like kind of sizzle around. It's like a little, it's like a whatever air hockey thing. Lithium will like spin around on the top of water. You drop a hunk of sodium in there into water, it'll depends on how big it is. If it's too big, it explodes. And potassium explodes faster, and rubidium explodes even faster. Cesium, you know, it's extremely reactive, and I mean, if you throw it in water, you better duck and run away because that thing's going to explode. So why is it that potassium metal, you can see potassium is slightly higher than lithium. So lithium's a better reducing agent, but why is potassium metal more reactive? It has to do including crystal structure and other things. So the potential, the reduction potentials correspond very, very closely to the activity series of metals, but it's not exactly the same. So this has to do with the potential of the atoms and the electrons within the atoms. This is not necessarily the raw, just chemical power of things. So potassium metal is more powerful than lithium metal, but If you have a potassium battery versus a lithium battery, the lithium battery is more powerful. But what's even better about lithium is it's a smaller atom. So it's a smaller atom, lighter atom, and it carries more of a punch, which is why lithium batteries are so awesome, because they're light, they're powerful, and they're light. So it's a wonderful thing. And a caution though, with lithium ion batteries, we'll talk about those probably not today, maybe Monday or Wednesday of next week. But I mean, hold up my cell phone. I mean, this has a lithium ion battery in it. And if maybe you've noticed that over time, your batteries don't work as well. And the reason is because the opposite direction. So when you charge up, well, actually for lithium ion batteries, you're just moving the ions. It's actually the lithium ions. But if you overcharge your battery, you get this reaction in the opposite direction. So you go, actually no, I guess it is this proper direction. If you overcharge the battery, you get that reaction right there where your lithium ions turn into lithium metal. And then the lithium metal reacts with the battery. Actually, it destroys the inside of the battery. And that's what makes the lithium ion batteries degrade over time, is actually most typically overcharging. So if you want to know how to protect your batteries, your lithium ion batteries, is to not overcharge them. And so although I'm doing this right now, I mean, I have my laptop hooked up and it's on the power supply, and the battery's just about full. And I mean, I know there's probably a little bit of damage going on to the battery right now on my laptop. But I mean, it's part of it is like the usage argument, because I mean, if the power supply goes out, I still need to teach, right? So I need to have the full battery. If I just run off the battery, it'll drain the battery in like, I don't know, like an hour or something like that. So I mean, it depends on your application. Sometimes you just can't avoid it. But I mean, what I try to do when I charge things up, I usually try to get it into like the 80s or 90s range and not charge it all the way up. So that way it doesn't overcharge. And because if you continually charge it to 100% or just leave it plugged in, you're like, oh, it's 100%, but it stays 100% for a long time if I supercharge it up. Yeah, but if you keep on doing that, the battery's gonna degrade. And I remember some of the old, before I knew about that, I would just charge everything up, super strong, and then like after year and a half, 2 years, the batteries never were they wouldn't hold a charge anymore because I was destroying them. So, but anyways, coming back to the standard cell potentials. So, and these are nice, these standard cell potentials. So our smart friends have done our homework for us, and all we have to do is copy their homework. So we have all these right here. And the standard cell potential, so let's look at this equation. The standard cell potential, E0 cell, the zero means standard, is oxidation plus reduction. So we have two half reactions. So when something is oxidized, that means it loses electrons. When something is reduced, it means it gains electrons. So we have electron transfer in this. And then the potential of the oxidation is just the opposite of the reduction potential. So having all these reduction potentials, if we need to have the oxidation potential, we just multiply it by -1. I mean, this voltage, the E0 is just minus E0 reduction is the oxidation potential. So let's do this for a problem. Use the tabulated standard cell potentials to calculate the potential for this reaction occurring at 25 degrees Celsius. This equation is balanced. So we have aluminum reacting with nitrate and 4 acids making aluminum ion plus nitrogen monoxide plus 2 waters. So let's start looking for them. So I have to use the chart, and let me find aluminum, and aha, here is aluminum right here. Aluminum plus 3 electrons is negative 1.66 volts. So, but if you look at the reaction, it's going in the opposite direction. We're going from aluminum metal to aluminum plus three electrons. So if you look at this one here, aluminum plus 3 electrons going to aluminum metal is negative 1.66 volts, but the opposite direction, going in the opposite direction, is positive 1.66 volts. So are you following that? Okay, so now, so aluminum is going, that was the easy one. Now we got to look for the nitrate and the nitrogen monoxide. So we got to go find this one up there, and let's see here, where is it? Oh, here it is. It's right here. Nitrate plus 4 hydrogens plus 3 electrons going to nitrogen monoxide and water. Do they even include water in that? Because it's aqueous. I don't know if they probably do. What am I doing? Stop. Don't move. So, okay, yeah, they do have water. So here is that. And it is positive 0.96 volts. So from the chart, you can see I've written there, it's on the chart. This, we don't put the negative sign here because the equation is written as is. So we don't have to, it's being reduced. So nitrate is being reduced. So the E0, the standard cell, so this is the E0 oxidation, this is the E0 reduction. It's easy, we just add them. So then this is 2.62 volts. So you just have to add them together, and this is our final answer. So meaning, if we had a standard cell that has this set up, if we had just like this cell here, here's a standard cell, but instead of zinc, we had aluminum there, and instead of copper, we had nitrate plus acid on there. If we did this and let it run through a voltmeter, it would be 2.62 volts. So, and the other thing you wonder how, like nitrate and hydrogen ion, these are aqueous. How do you make a standard cell of that? What is typically done is a piece of platinum is put, if you can see that, PT is platinum. You would put a piece of platinum here, and I wouldn't be copper colored, it'd be silver colored, but it just provides a surface for things, and platinum is very unreactive. So I guess you could use gold too, but platinum tends to be more reactive on the surface, so it's better it lets things move around on the surface better. So platinum is typically used, and then that's how you would run this reaction. And of course, there would be nitrogen monoxide gas bubbling up the top too, if you did that. So, but the important skill I wanted to show with this is to identify the half reactions, which you've seen before when we balance oxidation reduction reactions. And the other skill is looking at the chart, deciding what is being oxidized, what is being reduced. So, and then flipping the sign for the oxidation, keeping it the same for the reduction, and adding them together. So, questions with this one? So, okay. There is, you can predict if things are spontaneous or non-spontaneous. So here's an equation. The Gibbs energy, the standard Gibbs energy, is going to be minus NFE0 cell. So We'll get to this equation soon. N is going to be your moles of, I guess I'm too small, too big, I should say. N is your moles of electrons, and F is Faraday's constant, 96,485, that's a 6, coulombs per mole electron. So F is a constant, N is the number of moles of electrons. So it tells you something. If your E0 cell, if your standard cell potential is positive, the reaction is spontaneous. It's going to happen. If the E0 cell is negative, it's non-spontaneous. Does that mean that non-spontaneous reactions don't happen? No, they do happen. But you just have to put energy into it. And that's the idea of recharging a battery, right? So you have your battery, you do things, you play with you look on the internet, you play your video games, and the battery dies. What do? You plug it back in. And the positive E0 cell is pushing out electrons, and you're doing work on it. And when it comes time to recharge the battery, electricity potential goes into the cell phone or whatever it is you're using, your battery, and then it pushes the reaction the other way, recharging the battery. So recharging the battery, you are doing a chemical reaction and you're moving the electrons into their proper place. So, all right, so we can do this to predict if chemical reactions are going to be spontaneous or non-spontaneous. So what's going to happen if I put a slab of iron metal into a magnesium solution? So I go to my standard cell potential chart and I look for iron metal. So here is iron metal here. There's more than one. Here it is. Here's iron metal here. And there's also a magnesium. I should change colors. Here's magnesium, here's iron, and here's iron. So if we have, what's going to happen when we have iron metal plus magnesium plus 2? So in order for this chemical reaction to go to proceed to form magnesium metal, and I'm saying 0 for the 0 oxidation state, this means the E0 cell is going to be the E0 oxidation plus the E0 reduction, and that for magnesium, it's going to be opposite of this. It's going to be, oh, it's going to be reduced. I'm sorry, it's not going to be opposite. So for magnesium, it's written as is, so it's going to be negative 2.37, because that's being reduced, plus in the oxidation of iron, so it's either going to be the 0.036 or negative 0.045, either way, plus a positive 0.45. If you can see here, this is going to be close to negative 2. It's going to be whatever, negative 1.88. So it's going to be close to negative 2. Negative 2, the E0 cell, this E0 cell is negative. Since it's negative, that means that the delta G minus NF E0 cell, this is also negative. You can see this. So since if this E0 cell is negative, negative O negative is a positive. If delta G is positive, it means it's non-spontaneous. So this reaction here, as written, is non-spontaneous. So if I'm worried about, so why do I care? Let's say I'm a chemical engineer and I'm working in a metallurgy plant or something, or maybe I'm making Epsom salts. So Epsom salts is magnesium sulfate. And I have this iron tank. So I'm like, okay, I have my iron tank and I'm like, what can I throw Epsom salts? Can I use this iron tank to make Epsom salts? And the answer is yes, I can, because the magnesium is not going to corrode the iron. And then your boss comes to you and says, hey, you know what? I'm no longer interested in Epsom salts. You know what's really cool now is the Grecian formula. Have you ever heard of the Grecian formula? We need to start making the Grecian formula, and let's use that tank that you've been using Epsom salts in. And the Grecian formula, it's lead acetate. That's what's the Grecian formula. So what you then do is that your boss, who's a brilliant person, but studied art history instead of chemistry or something. That's the Boston Dilbert, studied art history. I'm kind of stealing it from that. And then you go and you look at your standard cell potential and you find lead. And lead here, so it's being reduced. So your E0 reduction potential is, as written, is going to be minus 0.13, and your iron and your E0 oxidation is the iron, it's positive 0.45. So you add them together and you get positive 0.32. So this reaction here has an E0 equals positive 0.32 volts, which means if you have an iron tank and you throw in the Grecian formula, it's going to eat apart the iron tank. And you will no longer have an iron tank if you keep on running this. So you have to tell your boss, no, I'm sorry, we cannot use our factory to make Grecian formula unless you want to build a new tank. And I am so good at chemistry, I can tell you, you can't use iron. If you give me a raise, I will tell you what you can put it in, what tank you can put it into it, so kind of thing. So that is like the simple version of what you can use this for. So, and in a kind of a juvenile thing, I mean, I know I'm probably showing my age, so Harry Potter is still cool. When I was growing up, one of the big things was the wrestling, the WWF wrestlers, and you always knew who was going to win. So whoever, it varied year by year. Andre the Giant never really lost. Very infrequently did Macho Man or Hulk Hogan. If Hulk Hogan fight the Undertaker, Hulk Hogan's going to win. There was, and it was, the rest was just theater, kind of thing. And this is just like the wrestling federation. So the best wrestler of all times, depending on which way you want to look at it, this is like Andre the Giant or something like that, is lithium, or something. Oh no, I guess he would always lose. I don't know. Who's in the $1 Million Man? He lost a lot. So that's like the $1 Million Man is like lithium or potassium. And then one that always won, copper. Copper is up here. Copper is like Hulk Hogan. So when these two metals fight, the question is lithium going to be able to rip the electrons off of copper? And the answer is no, but copper can rip the electrons off of lithium. So I always kind of like, when I was learning this, I was kind of like going back to the good old days of the World Wrestling Federation. And I know they changed it, and then I know that it was something else, and The Rock was in it too or something. I stopped following it after The Rock started wrestling. So it changed the name. It was no longer WWF. It was, what was it? Something, I don't know. Oh, it is? Okay. I don't know. I don't know. That's the way I always saw it. I always made me think of professional wrestling for some reason. And, professionally wrestling, of course, is not really that professional. Yeah, it's not like boxing or something like that. But okay. So, are there any questions? So, a new conceptual thing. Which metal dissolves in nitric acid but not hydrochloric acid? So, if you look at these, the questions are iron, gold, and silver. So let's go find them. Iron's already highlighted, so it's there in red. And here's silver, and I'll change colors. Here is silver. And where is gold? Here's gold. And I'll do pink for gold. And then I'll put another important reaction. I will put in blue this one. Okay, so you can see, and I guess I normally talk. If here is iron right there. So, and if you look at it, it is below right below the hydrogen zero line. It's right below the zero line. And so iron is one of those metals that will dissolve in acid. So that means that iron will slowly dissolve in any acid, quickly in a strong acid, slowly in a weaker acid. So if you take an iron nail and you stick it into a jar of vinegar, and if there's enough vinegar, the vinegar will eat the nail down. So, but if you put silver, in a slightly acidic environment, like a jar of vinegar, it will not dissolve, and actually neither will gold. And another slightly acidic environment that we have is our mouths. And what do we make dental implants out of? We make them out of silver and gold and mercury. So is mercury on this list? No, it's not. Mercury is above. So mercury does not dissolve in acid. So I have mercury amalgam fillings in my teeth. Or some of my teeth have mercury amalgam fillings, and they're still there. Actually, mercury amalgam fillings, they last a really, really long time. So because acid doesn't dissolve them. So in fact, well, acid dissolves your teeth. So actually the fillings can potentially last longer than your teeth. But our teeth also remineralize. So it's not like our teeth just slowly get thinner as we age. Our teeth actually do remineralize, but the point though is that you don't need to necessarily come back after a few years and add more mercury to your filling. It's not going to dissolve in your mouth. So okay, but then going up though, here's the nitric line and gold. So but if you see silver is, keep on drawing this up, silver here is below that long blue nitric line, which means it's going to react. So silver and copper and mercury will dissolve in nitric acid, but not gold. You throw gold in nitric acid and it doesn't dissolve. And so this is a big deal because gold is very unreactive. And that's one of the things that, one of the reasons why gold is so coveted. So if you look at economics and metals, so if you look at the expensive metals, they're usually the noble, the unreactive metals. So if you think, what's an expensive metal? I mean, most people just say off the bat, it's like gold. Gold is the most expensive metal. That actually platinum is more expensive, but it's not because of necessarily of the rarity of it, or it's partially the reactivity. Platinum metal is very unreactive, but it's also used as a catalyst. So platinum is useful. There's much more platinum than there is gold. So the platinum supply on the earth is higher than the gold supply. So it's easier to find platinum than it is to find gold, but platinum costs more. Why? Because it's useful. I think if I had to guess, the most expensive metal would probably be weapons grade plutonium, or maybe some of the uranic elements, the super heavy elements. Those are hard to make, but they're not necessarily very useful, except for maybe californium. So, but I mean, you can't really use them for anything. Californium and plutonium, though, you can use for nuclear weapons. So, and that's what makes it so expensive. So but plutonium, I don't know about californium. Plutonium is very reactive. It's a reactive and toxic metal. So, so it's not very unreactive at all. But anyways, this goes back to where things are. The gold here written in pink is above that nitric line, so that means it's not going to react. Silver is below that nitric line, so it will react. But silver is also above this hydrogen line. So since silver is between the hydrogen line and the nitric line, it will not react in most acids, but it will react in nitric acid. And so does anybody know how you get gold and platinum and anything else to dissolve? There's something called aqua regia, also known as the water of life, aqua regia. And it's a mixture of hydrochloric and nitric acid. It's a 3-to-1. I think it's 3 parts hydrochloric to 1 part nitric. Well, it's either one of the two. I know it's 3-to-1 nitric, hydrochloric. I forget which one it is, but if you make aqua regia, you can dissolve platinum and gold in it. It's a very slow reaction. So, and it's hard to do, but you can dissolve gold. And if you remember, chemistry kind of started with the alchemists. Have you heard of alchemy before? So the idea turn lead into gold. So a lot of the chemical symbols and meaning, a lot of it comes from alchemy originally. And so the water of life, I mean, you shouldn't drink it. It's not going to give you eternal life, but it's a mixture of hydrochloric and nitric acid because it dissolves gold. And there are some stories with this. So some of the Germans, like when the Nazis would invade places, I mean, if you see what's going on with the looting and whatnot with Russia, I mean, it's very common that invading armies take things. So, there were some scientists that won the Nobel Prizes. And when you win the Nobel Prize, you get a couple things. One of them is a gold medallion. And they didn't want to turn over their gold medallions to the Nazis. So what they did was they dissolved them in aqua regia. So when they heard the Nazis are coming, what did they do? They made aqua regia and they threw their Nobel Prizes into aqua regia, dissolved it. So of course, a stormtrooper. Those are the Nazi foot soldiers are called stormtroopers. So the stormtroopers came like, "Where's the gold?" And like, "Well, I don't know." Like, "Well, I'm gonna look through your lab." Like, "Go ahead." They're not going to look at that solution and say, "Is that aqua regia?" No, it was gold solution. Also, this tells you like you can plate things in gold very easily. We'll talk about electroplating later, but there are kits you can buy that will plate gold. And what they do is you have gold ions in solution, and if you dip whatever it is you want to gold plate, like a pair of earrings. So if you have a crappy pair of earrings you want to turn into gold earrings, you just dip it in the solution. It's got gold ions. And how did they get gold ions? Aqua regia. They took a gold metal and dissolved it in aqua regia. So obviously though, so if you have gold metal is very unreactive, but the opposite is true. Gold ions are extremely reactive. Just like down here, lithium metal, potassium metal, very reactive. Potassium ions, lithium ions, very unreactive. So they're always inverses. And then in the middle is kind of even. So like lead and iron and tin They're medium strength oxidizing, medium strength reduction. So it depends on the environment, if it's reactive or not. Okay, so does that make sense? Okay, and so we're gonna go back to this equation. The standard Gibbs energy change, delta G0, is equal to minus NFE0 cell. So there's a couple things about chemistry. So like now when we take chemistry, we take it as one class. So like I mean, so chemistry grew up independent of each other. So like as we were learning chemistry, someone didn't come and say, okay, this is all chemistry, we should all learn together. No, what happened was things were developed independently, and each branch of chemistry got its own notation, and they had their own way of doing things. So Gibbs, when he did his calculations and his derivations, he thought that negative means spontaneous, positive means non-spontaneous. And then when electrochemists were coming along and doing all this, they wanted to have positive be spontaneous and negative be non-spontaneous. So they wanted to be more positive than Gibbs. And so that's the reason why these equations, that's why we need to have a negative sign. It's just they were developed independently of each other. And also one of them, this constant, the Faraday constant, that constant is named after Michael Faraday. And Michael Faraday is another, there are some scientists, if I met them, I'd like to punch them in the face. So Heisenberg is one of them. I would love to punch that guy in the face. Baer is another one. I'd like to punch that guy in the face. They're both dead. I can maybe, slap some water on their gravestones or something like that, But Faraday, though, I'd love to have lunch with him. Another one, Schrodinger, he's another guy I'd love to have lunch with. He's a really cool guy. I mean, but Faraday, he was British, he was English, and he was actually a commoner. And of course, I mean, we're all commoners, but I mean, this is, post-American War Revolution, kind of thing where we can make our own destiny of sorts, but at the time, pre American Revolution, and it was much harder for a commoner to rise to like a nobility sort of a level, and Faraday, he did it. So he's the exception, but he was, among other things, he was an entertainer, and a lot of scientists were entertainers. Ben Franklin, he put on shows. So Franklin was a scientist, and he was also, I mean, he was many things, but he would put on like various shows with his science stuff. So it was almost like going to a circus kind of thing. Same thing with Michael Faraday. What Faraday was trying to prove, he was trying to prove that electricity was the same thing as light. And he did it, he was able to connect them. So major accomplishments. And to honor him for that, we have the Faraday constant. And we still call it the Faraday constant. And the Faraday constant is that a mole of electrons, if we have a mole of electrons, 6.02 times 10 to the 23rd electrons, those electrons have a charge of 96,485 coulombs. So, and like an amp is a coulomb per second. So when we are doing electricity, when you hear the word amp, an ampere, I mean, we use it today, right? I mean, that's our current flow is an amp. And how does an amp connect back to electrons? By the Faraday constant. So we need to use that. And N, what is N? N is the moles of electrons transferred. So let's relate the stuff from chapter 19 to chapter 20. So that's another theme I've been having in my tirades. Everything is connected. Everything is connected, and thermo is connected to electrochem, is connected to equilibrium. So all these things are connected. And we're going to connect chapters 19 and 20. And that's another reason we we do this in this order. You have the you don't have to do it scattered. We do equilibrium and then energetics first, and then we tackle electrochem. So, well, I guess I should go back so you can see the equations. Use the tabulated standard potential electropotentials to calculate the standard Gibbs free energy change for this reaction. Iodine plus 2 bromides makes 2 iodides plus bromine. So you look up the reduction potentials and you have it written as such. So here are the reduction potentials. Iodine plus reduced to 2 electrons to form iodide is 0.54 volts. Bromine plus 2 electrons to form 2 bromides is 1.09 volts. So what are the half reactions for this reaction? We have iodine plus 2 electrons goes to 2 iodides. And because I'm looking at right there. And how am I getting the electron transfers? So the oxidation state here is 0. The oxidation state here is -1. So to have 2 iodine atoms at a 0 oxidation state, they need 2 electrons to form 2 iodides at -1 oxidation state. So you need 2 electrons for that. And the other half reaction is going to be 2 bromides forming bromine plus 2 electrons. So the bromides are the source of the electrons. So this reaction, the top reaction, ooh, what the heck? Why did it go up there? Top reaction, we just write it as written. The iodides, it's going to be positive 0.54 volts. And the other reaction is going to be 1.09 volts. So it's just, as written. So what is this going to be? This is going to be 5. Is that 0.45? Is that right? No, it's not. It's 5.5. It's 0.55 volts. So, am I doing this right? Yes, I'm doing this right. It's easier for me to do it the other way around. 0.54 minus from 1.09. That's what I should have done. Been trying to add negative numbers. So, okay, so the E0 cell is, no, I'm sorry, it's negative. What am I doing? Positive. It's going to be negative. The wrong sign. So this reaction is negative 0.55 volts. So we look at this reaction here. I'll go ahead and copy it. Let's make it easier on you guys. So delta G is going to be how many moles of electrons are we transferring? We are transferring 2, so minus 2 moles of electrons. F is 96,485 coulombs per mole electron. And our standard potential is minus 0.55 volts, and a volt is a joule per coulomb, minus 0.55 joules per coulomb. And if you look at the units, moles of electrons cancel, coulombs cancel, and whatever this is, going to be positive 200 kilojoules. Okay. Oh, wrong about the number. 100 kilojoules. So this equals positive 1.1 times 10 to the 5th joules. So, and then here is our final answer. Okay. So let's look at this. Okay, let me back it up. Recap for this one. We have this reaction here. Iodine solid plus 2 bromides makes 2 iodides plus bromine. So is this reaction spontaneous? So we have to calculate the delta G0 and relating delta G is calculate the delta G0 for this reaction. So to get the delta G0, we need the E0. So we look up the standard potentials, and the standard reduction potential for iodine is 0.54 volts, and the standard reduction for bromine is 1.09 volts. Tracking this reaction, looking at the half reactions, iodine is being reduced, it's adding electrons. Bromide or bromine, if you will, the element is being oxidized. So when we assign the potentials to this, we leave it the same for iodine, but then we put it the opposite sign because that's the oxidation for bromine. And then when we add them together, the standard cell, this is going to be 0.55 volts. And I'm sorry, negative 0.55 volts. Then we throw this into the delta G0 is minus NF E0 cell. We've calculated E0 cell to negative 0.55 volts. Volts is joules per coulomb. And we figure out that 2 moles of electrons are being transferred. And then the Faraday constant. So using this, we get a positive 1.1, so 110 kilojoules per mole reaction, positive 110 kilojoules per mole reaction. That means that this reaction is not going to happen spontaneously. So this reaction is non-spontaneous. So questions with this so far? So coming up soon, we might get to it today, non-standard conditions. When you look at moles of electrons, when you do the moles of electrons, whenever you're looking, when you're looking at electron transfers, and when you balance it for the moles of reactions, moles of electrons, you do not multiply the standard cell potentials. You do not multiply them by those numbers. So, and I know this is confusing for you as a student, because when you have the standard enthalpy, standard entropy, standard enthalpy, all these things, you always multiply it by a certain factor. For electrochemistry, you don't. So, and the reason is because the standard electron, the electromotive force, the EMF, it only matters by the elements. So it is only by the electrons and how they're attached to the atoms. So it doesn't matter if you have one atom or if you have an ocean of atoms. The electromotive force for an electron, moving an electron off of one atom, off of a million atoms, the amount of force that it requires for each electron does not change. So, and that is one of the more common mistakes, and that's coming up soon. Not right now, but soon. So let's see if you can solve this reaction right here. So we have bromine liquid plus 2 iodides make 2 bromides and iodine. So what is the standard Gibbs, the delta G, the standard Gibbs free energy change for this chemical reaction? And there's the data that you need. There's a shortcut on this one too. You're gonna kick yourself when you figure out what the shortcut is. Did you need more time? Okay. Everything else you got. Okay, so everyone seems to be converging. Kiana, do you have any questions?
No, I'm all good.
So answer C. And, you know, you probably could have picked that one without doing any math. Do you know why? Yeah, it's the same problem, but the other direction. So you would just flip it. Yes. So, but you did some math, so you did the long way, huh? Or did you just look at me like, man? Yeah. Okay. All right. You found the shortcut. And laziness, the proper type of laziness is rewarded in science. So I'm not complete laziness is rewarded, but the proper type of like, meh. Let's see what else someone else has done. All right, so here is a derivation. So we're going to start going into some non-standard conditions. So standard and non-standard. We have, so delta G0 is equal to minus RT ln K. So delta G0 is also equal to minus NF E0 cell. So you can set these equations equal to each other, and you can also then write your E0 cell is equal to RT over NF natural log of K, K being the equilibrium constant. And if you want, you can put in R. R is 8.314 joule per mole Kelvin, temperature 298 Kelvin, Faraday's constant, and this one right here, this natural log of K, converting to 2.303 log K. This is the change of base formula for logs. I don't know, what always amazes me about science, all those stupid math formulas that you learn, you think, I'm never going to use this. Never. And you're like, then you use it, you're like, oh crap. That's what I've learned about all my math. I just like, well, have you learned Green's theorem yet? Or you haven't? Yeah. That's when you have an integral, you have a surface, and then you loop around the surface. If you integral the path as you're looping around the surface. And I remember doing that. I was like studying, I'm like, yeah, I'll never use this, kind of thing. I was just like, I remember studying this and taking a test. I'm like, guess what? brain dump, forgot everything, you know, gone from my memory, you know, kind of thing. And then I started studying quantum mechanics, and they're like, and then Green's theorem. I'm like, what? Green's theorem has an actual, you know, application, you know. Anyways, so this is from the log change of base formula, and yes, it has an actual application, and actually 2.303 is the natural log of 10, if you're wondering. So and you can combine this to have this E0 cell is equal to this right here, 0.0592 volts over the number of moles of electrons transferred times the log of K. So couple things with this. Why are we using log base 10? And the reason is because back in the day, you know, freshman chemistry was written like this course as is, with the exception of a few things in quantum mechanics, was mostly written this way in 1960. So Linus Pauling. In 1960, we didn't have, you know, we didn't have sweet calculators, you know, that we carried around with us everywhere that, you know, has more computing power than the Apollo spacecraft that went to the moon and back, right? So we have all the information, and this is connected to the internet, so I can find anything I want, you know, using a cell phone. We didn't have that back in the day. What they had were logarithm tables and slide rules. So like a lot of the things like when you raise things to powers and all that stuff, and when you do a lot of these calculations, I mean, it's easy this day and age. We just throw in our calculators and like think nothing of it. But back in the day, when you wanted to find something, you'd have to look into a chart, and then to figure out the logarithm stuff. And there's log charts and there's natural log charts. Log is log base 10, you know, and it's kind of like, why should I carry 2 books when I can carry 1? You know, so that's why they converted this back into log base 10. So it's because back in the day, you literally had to carry a bunch of books with you. So, and so, but that's the reason. So that's the reason why we have that formula written as is, and that's an important one. We'll get to another example. We can then look at non-standard. So delta G is equal to delta G0 plus RT natural log of Q, Q being the reaction quotient. That was a previous chapter equation. We're just doing the derivation here. Oh, you're highlighting. Okay, you're fine. Okay, so delta G is equal to delta G0 plus RTL and Q. We can plug in NFE cell. So notice that this one is missing a 0. It's a standard Gibbs, so it has no standard. Whereas these have standards, and we all have standards, right? But this is non-standard. So then the E cell is E0 cell minus RT over NF natural log of Q. And if we are going to stick to all the other terms, 25 degrees Celsius, Faraday's constant is changed, it doesn't change, R doesn't change, then we have this equation here, and this is known as the Nernst equation. So it's the non-standard, still at 25 degrees Celsius. So when you're not at 25 degrees Celsius, you have to change this, and the Nernst equation is no longer used. So, a lot of people use the Nernst equation. So they use it quite a bit in marine. So for both like maritime vessels and boats, and also the Navy. So Navy uses more steam tables, but you see it quite a bit in marine, marine, like the maritime, like the, you know, boats that float kind of thing. So in a lot of the civilian stuff, I had a lot of students that when I was teaching this, like, oh yeah, we learned about that. You know, like we learned a Nernst equation. we did it when we were deciding what kind of paint to put on boats and stuff like that. So it's big on corrosion. So, and it's specifically for application of what you can connect to what in boats and how it deals with corrosion. So because when you have dissimilar metals touching one another, you can create a galvanic cell, a voltaic cell. And then because of that, things can corrode. And if you have a boat floating in water, you don't want the boat to corrode underneath it and then fill with water, kind of thing, right? So the maritime folks that work in water know this, so they're very careful about what kind of metals touch other metals. So that's the Nernst equation. So how much we got? 5 minutes left. I don't know if I'll finish in 5 minutes. I don't think I can. So I think I'll pick up here. I do have some stories to tell, I guess. I wanted to tell some stories. Did I tell you guys I mean I'm an American. I grew up in the United States, but I used to live in Hungary. So yeah. What? Oh, I was a postdoctoral fellow, so scientist, and I worked. I'm going to butcher it in Hungarian. I worked for the Magyar Tudományos Akadémia, so that's the Hungarian Academy of Sciences, the Chemikai Kutakutzpont, that's the Chemical Research Center. So, but what's interesting about it is I mean, Hungary used to be part of the Soviet Union. So, and it was interesting. I was there in 2006. And I visited twice since then, in 2012 and 2019. It's interesting to see how Hungary has changed since, I mean, even in the time I've seen it, and in like like I get, well, at least some of it, I get some of the Soviet Russian sort of culture because it was very prevalent in Hungary, you know, because of that. And it's, and to me, at least, like what's going on with Ukraine, and some of it I find funny, but I mean, because I mean, part of it is the cultural aspect of it. But I don't know if you, I've been quasi obsessed looking. Are you guys following the war at all, or not really? Okay, yeah, I've been mildly obsessed, and there's been reports, which I think is kind of funny. Like, I mean, Russian soldiers have been looting, and some of the things they're taking washing machines, but one of the more interesting things, they're taking underwear. So, well, they do. So the thing is, like with so in the Soviet Empire, the Soviet Union, like, so you have to understand how communism works. I mean, everyone gets the same thing. Like when communism fell, and like, so when you took people from the USSR to the United States, some people loved it, some people hated it. The people that hated it were they said there's too many choices. So the example they give is milk. So when you're in the Soviet Union and you wanted to go buy milk, you went to the store and they had one type of milk. What happens if you go to Safeway or Foodland and say, I'm gonna buy some milk? Like, well, you've got organic, you have glycerine, right? You have 1%, 2%, you have skim, you have organic, you have coconut milk, you've got almond milk, you've got, I don't know, I've even seen, what is that, the cashew milk, right? There's just like, there's so many choices, and these people that are just used to one thing. And when like the factories, when the factories made clothes, they made one type. Everyone got the same jacket, everyone got the same pants. I mean, they had underwear, but it was just everyone had the same. So it wasn't, there was no like, and actually it bothered, so the people that wanted more fashion, when they see the Western fashion really, really important, or was really, really important to the Soviets, because they're like, wow, it's not the stuff like, and you can spot someone like I, as an American, I stood out like a sore thumb because I mean because I dressed differently, and I remember in 2006, maybe it's still true. Like usually when you're traveling, you can spot Americans like that, just because, yeah. And body language is different. Body language, dress, it's also okay. But yeah, all right. So that's done. Story time now. So yeah, so you've noticed that too. So it's not just in Europe, huh?